All right. Welcome, everyone. So it's my absolute delight to introduce this Rosenthal lecture. So this is the 45th Hanan Rosenthal Memorial Lecture in Atomic Physics. We have the great pleasure and honor to have Professor Lund University, who is going to give this lecture. But I'm going to give to Steve to introduce her. What I'm going to do is, for the next minute, I'm going to give you a very, very quick history of what's behind this lecture. So it's actually interesting because there's only bits and pieces that are available. But the idea is that this lecture was named after Hanan Rosenthal, who was born in August 21st, 1971 in Tel Aviv. There are only bits that are known about where the family was, but they moved quite a lot during the children's childhood. They stayed for a year in Germany in 1956. They moved to the US, to Portland, Oregon in 1957, which is actually the time where that picture was taken, where you can actually see Gerda and Alfred, that are Hanan Rosenthal's parents. The young man is Hanan Rosenthal, and the sister is Naomi, which we're still in touch with. So this is quite moving. Hanan Rosenthal was a graduate student at Columbia and an instructor in physics at Yale, where his specialty was atomic physics. Now, tragically, he passed away young at the age of 27 in the 30th of June, 1971. So 2 years after his passing, the memorial lecture was actually started in his name, started in 1973. And so the idea is that at the time it was spread between Yale and Columbia. In the past few years it has been held at Yale exclusively. And we've had the pleasure and honor of having many, many distinguished people coming to give this lecture, including the first one, which I understand is actually going to be mentioned during Anne's talk, Hugo Fano, which was a towering figure of quantum mechanics in the early 20th century. And then, as you can see, there's a long list of people who have really built the modern history of atomic physics. And the people in bold are people who got the Nobel Prize, which is very interesting because in most cases, people give the Rosenthal lecture before getting it. But Anne decided first to get the Nobel Prize to then give a more prestigious lecture. And with this, I will let Steve give a more serious introduction of Anne.
Okay, thank you very much, Nir. So we're very fortunate to have Anne. She's a little bit busy, and by happy coincidence, she said that she and her husband, Klaus-Göran Wallström, who's also here, on a long trip to Canada and California, and they graciously agreed to stop in on their way back to Lund University in Sweden, where they both are members of the physics department. Anne was born in France. Undergraduate at ENS, did her PhD work at Pierre and Marie Curie University and the actual research at CEA Saclay. She's received a long string of recognitions for creating, the world's shortest laser pulses and using those to sort of take stop-action flash pictures of what electrons are doing inside atoms. And in 2022, she and two other people with whom in the same field won the Wolf Prize, and the same trio the next year won the Nobel Prize in 2023. So I'm very excited to welcome Anne Villiers, and we'll hear about life in the fast lane.
Thank you very much. So So, and let me start by a very simple introduction. This is an arrow of time just to tell you what are we talking about. We start by the age of the universe, which is approximately 10 to 18 seconds, and we go to the attosecond, 10 to minus 18 seconds. And here you have a few timescales, timescale of humanity, astronomical timescales. Below you have the second, the heartbeat, millisecond, typical mechanical times, nanosecond. Femtosecond is the time for atoms to move in molecules and led to a Nobel Prize to Ahmed Zival in chemistry in 1999. And attosecond is the time of that you need to catch motion of electron in atom. Let's do Nobel Prize to Pierre Agostini, Ferencross, and myself, 2023. So this is the outline of the talk. First, I'm going to tell you about high-order harmonic generation, then attosecond pulses, and finally how we use these pulses to study electron dynamics. Let me start by 1960, the invention of the laser. Nothing will have happened without the laser. And what we're going to use in this research is the fact that you can confine laser pulses in short pulses, and also that it's intense radiation. The invention of lasers opened new areas in physics. One of them is nonlinear optics. Here you have the first setup that were used by Peter Franken, 1961, to demonstrate second harmonic generation in a piece of quartz. So you see, you use the laser focusing lens, some optics to analyze the radiation, and then a photon detector. And he could observe the generation of the second harmonic of light. Another field that was opened thanks to the invention of the laser is very fundamental: atoms in strong laser fields, multi-photon processes. Two photon excitation processes were predicted theoretically by Maria Goeppert-Mayer in 1931 as an exercise in the newly discovered quantum mechanics. Very, very interesting. But they could be observed only thanks to the invention of the lasers. In the 60s, Russian scientists studied multi-photon ionization. In 1979, Pierre Agostini and his group in Paris observed what is called above threshold ionization, where atoms can absorb more than what is needed for the ionization. For example, here, one more photons. And you detect that by looking at the energies of the electrons that are being produced. And my own thesis work, we are in the beginning of the 80s, was multiple ionization processes by multi-photon absorption. Here you see the creation of xenon 2+ by absorbing many photons. So at that point, it was kind of clear that yes, in this process we create excited atoms, excited ions. Would be interesting to look at the fluorescence emitted by these excited species. So we set up an experiment where we sent an intense laser. It looked like this, very old, with 40 picosecond pulse duration. You have the oscillator here and two amplifiers. So we send this laser into a gas jet of atoms, rare gas atoms, and we look at the radiation using a grating and a detector. This is a picture of that experiment. Looks also very old, I must say. The laser is coming from the right. There is a lens here. This is a vacuum chamber. And as a proof that we really wanted to look at fluorescence, we actually had two detection axes in the perpendicular direction, grating here, a detector, and also along the propagation axis grating in that chamber and a detector. You can notice that we used a printer here to record the signal. So this is really old times, before any computer. With the pen was coupled to the detector, and then the routing was rotating. The grating was rotating, and the paper as well. Yes, I mean, the young people here can't imagine these things. We never saw anything along the perpendicular direction. We saw radiation emitted really collinearly with the laser field, actually in a very narrow cone. And this light was in the form of high-order harmonics of the laser field. You see here in argon from harmonic 13 to 31. Only odd orders. This is due to the symmetry of the interaction, which kills even orders. If we plot the intensities of this harmonic, you have this characteristic behavior with a plateau where all of the harmonics have approximately the same intensity, and this distribution is ending with a cutoff. This plateau behavior was really the discovery, because at the time we were thinking in terms of perturbation theory, where you expand the polarization in the medium as a series of powers of the electric field. But for such a series to be valid, you want the first order to be much larger than the third, much larger than the fifth. And this was obviously not the case. So a very nonlinear phenomenon and non-perturbative. Where are we in the electromagnetic spectrum? We start from a laser in the infrared, and we multiply by a high number. We end up in the extreme ultraviolet region of the spectrum. Light is invisible and strongly absorbed by matter. Now I have a slide a little bit for the non-physicist, okay? I'm sure that you have heard about harmonics in connection with music, and we can actually make a comparison here between the harmonics that you get when you play violin. You get not only a certain tone, but harmonics. This is what makes the clang of a music instrument. And here is a harmonic spectrum due to the interaction between atoms and laser pulse. In both cases, we have a strong interaction here between atoms and laser, and the string of the violin and the bow. Of course, different type of waves, acoustic waves and light waves, different frequencies, but a similar phenomena. To understand the generation of these high-order harmonics, you need to do a little quantum mechanics to understand the response of a single atom to the radiation field. This is described by the Schrödinger equation, as you see here, with an atomic potential and the laser-atom interaction, which we describe using the dipole approximation. And it's generally fine to use a classical laser field. The difficulty in this problem is that this interaction is strong, is comparable to the atomic potential. But you also need to consider the response of the medium. This is described by Maxwell equations, which can be simplified by a wave equation. Physically, you want that all the atoms in the medium emit waves which are in phase. This is called phase matching. So you also need to solve this equation here, where you have the medium polarization, and this is the field that is generated. So it's really a combination of atomic physics and nonlinear optics. And actually, the first attempts to simulate these processes were by solving numerically both equations. Attempts that were successful doesn't mean we understand the physics behind. Huge progress in laser technology in the beginning of the 90s with several inventions. The Chirpers amplification technique, which led to a Nobel Prize to Gérard Moreau and Donna Strickland, 2018. This is a way to amplify short laser pulse without breaking your material. Also a new laser material, titanium sapphire, and a new technique to produce short laser pulse. And in particular in Europe, in Lund, they built a laser system using this new invention, and Sune Svanberg and Klaus Göran that is here. So in parallel, you have progress in instrumentation. We build dedicated equipment to study high-order harmonic generation. Here you have an old photo of myself with my first PhD student in France, Philippe Balcou, and we built the instrument that you see here, which contains basically the same elements I have already introduced. A gas jet, optics to analyze the radiation, and then a photon detector, in this case an electron multiplier. You see the side of the equipment, and it's a vacuum because the radiation that we produce does not propagate in air. You don't see the laser, it's behind the wall. At the time, we were using a neodymium glass laser system, 1 picosecond, 0.0 Hertz repetition rate. It was extremely slow. So when I heard about the laser system in Lund, we say, oh, we were invited to come to Lund, so we moved this equipment, and myself and Philippe and another PhD student to do experiments in Lund with very nice results. You have here one of the, so this is the characteristic of this new laser system. Main difference here is the repetition rate, which really allowed us to study this phenomena in a completely different way. In addition, this is the time where computers arrived in the laboratories, where we have personal computers that were that big with floppy disk, but we could really acquire data in a completely different way. This is an example of spectra obtained in helium gas. You see really high-order harmonics, up to 93 in this case, and a beautiful plateau behavior extending to much lower frequencies. So now I'm coming to the second part of this talk. What is the connection of these high-order harmonics with attosecond light pulses? So the idea was proposed, I would say, soon after the discovery of high-order harmonics. And it's illustrated on this cartoon. What you have is 3 harmonics. So what is represented is the wave of the electric field. If we assume that these harmonics are phase-locked, which means they have the same phase at a certain time, because of the periodicity, which is half, after half a laser period, then the minima will be in phase, and then the maxima, etc. So if you sum these 3 harmonics, you get a train of short light pulses. Half a laser period is 1.3 femtosecond. So you see that we are in the range of sub-femtosecond. We are in the attosecond time scale. What is shown here is the intensity of this attosecond pulse. If you sum not only 3 harmonics, but 10 harmonics, what do you get? Even shorter pulse and more intense, under the condition that this phase locking is valid for all the harmonics. So why do we get short pulses? Sorry, it's... No, let me say it. We get short pulses because we are in the extreme ultraviolets, so the period of light is short. We have a broad bandwidth, many harmonics. The question is, are the harmonics phase-locked? And it's going to take us, the community, actually 14 years to really show experimentally that yes, we had attosecond pulses. Breakthrough in 1993, a theoretical breakthrough by Ken Kullander, Ken Schaefer, Paul Korkum, and also Maciek Lewenstein and co-workers, proposed the three-step model that you see here, which gives an intuitive picture of the interaction between light and matter. So what you see here is an atomic potential which is strongly deformed by the laser field, by the laser atom interaction in one direction, the direction of the laser polarization, so that this wall is going up and the other one is going down. So this gives the possibility for an atom, for an electron here in the ground state, to tunnel through this barrier. Then the electron is free. It's being driven by the laser field. The laser field change of sign. It's driven back and acquires kinetic energy. And then there is a certain probability for the electron to recombine back to the ground state. And in this process, you have emission of light with high photon energy. This is a quantum mechanical process. So if you think in terms of electron wave packet, what you have is that part of the wave function is tunneling through, moving away, and this is several nanometers, coming back and recombine, interfering back to the ground state, so fully coherent process. So now I have a light version of this, a little bit for the undergraduate students here. So I hope you are with me. And this is called The Adventure of an Electron in the Laser Field. Okay, I'm talking mostly to undergraduate students. Are they undergraduate students? Yes, okay, good. So this is the electron in a prison. Very strong force between the nucleus and the electron. It's good, otherwise we would not exist, right? And on the sides you have a roller coaster. So the electron would like to have fun. What does the electron do? I see this. No. So the electron tries to escape, right? Everyone agree with that. How? Come on, be a little bit creative now. I can't hear. You have to speak louder.
Like breaking out of jail.
No? Tunneling, yes. Absolutely. Yes. This is called tunnel ionization, and this is in Swedish. This is why you have K instead of C and this I. Okay, the electron is in this roller coaster. It is having fun, and it's being accelerated and decelerated. So here is gravitation, but it's actually very similar. It's the electromagnetic force due to the laser. This adventure is finishing very bad, and it's shown here. The electron meets on its way, on its trajectory, the open prison, and it's falling into the prison. It's a recollision, and it's liberating its energy as a scream. And this is our attosecond light pulse. Okay? All right, and I'm going back to more serious. If we look at really now what is the connection between these attosecond pulses and the high harmonics I started from? We look at the different possible trajectories. There are different colors here to show that the electron comes back with different kinetic energies. Actually, at slightly different time, which means they are not coming back exactly at the same time. There is differences, but this is within tenths, hundred of attosecond, so short pulse. In the frequency domain, we have a broad spectrum. This is our plateau. This is the interpretation of the plateau, that it's a short pulse, broad spectrum in the frequency domain, and the probabilities for these different trajectories are very similar. Now, this process is repeated first on the other side of the atom, leading to an attosecond pulse with actually the opposite sign. And this leads to a modulation of the frequency spectrum with 2 omega difference here. And this is repeated many times depending on the pulse duration of your laser, and this leads to sharper harmonic peaks. And these peaks are corresponds to the higher order harmonics of the laser field. So you see that we have now interpreted or understood the physics in the time domain, and then we can go back to the frequency domain and we recover our high order harmonics. This is very similar to multiple diffraction through slits, similar to diffraction through multiple slits, leading to interferences in the far field. Here we have temporal slits. This is our attosecond pulses, leading to interference in the frequency domain. Let me say a few words about phase matching. How is phase matching achieved? So to achieve phase matching, we would like the refractive index of the fundamental field to be equal to the refractive index of the harmonic field which are generated. Is it possible? If we look at the kind of general variation of the index as a function of frequency, we know that it's larger than 1 in the visible range or near infrared range, and actually below 1 in this extreme ultraviolet part of the spectrum. So if you just look at this, the answer is no, phase matching is not possible. Fortunately, we also have ionization that takes place, so some free electrons actually never come back. They just leave and contribute to a medium which is partially ionized. Thanks to that, we add a negative term here to the refractive index at the fundamental frequency. So this point here goes down and you can achieve phase matching. This happens typically for a degree of ionization which is a few percent. So if you have too high intensity and increase too much this degree of ionization, then you ruin phase matching. So there is really a small window of intensity. You need to have a strong response of the atom, giving rise to these high harmonics, but not too high intensity, not to ruin phase matching. Just a small disclaimer here. In reality, it's a little bit more complicated than just dispersion in the gas and free electrons. There's also influence of focusing on and electron trajectory. Now move to the end of the 90s. We work on learning more and more on these harmonics in order to be able to answer the question, do we have attosecond pulses or not? And here is an experiment performed with my first PhD student in Lund, Mette Gårde, Ted Hensch. I don't remember if he was in your list. No, yes, he was. Okay. and Marco Bellini from Italy. This was European collaboration. And here we look at the coherence of the harmonic radiation. To do that, we create two sources from the same laser, and we just look in the far field. Do we get interferences or not? Very simple experiment. And this is what we get for harmonic 15. Well, I hope you see the interferences. Yes. You also see that there are two contributions. You have a collinear contribution and then a more divergent beam. If we change the delay between the two sources here, you get this image here after 15 femtosecond, where the interference have disappeared for the outer part while they are still present for the collimated part. And this was really the experimental demonstration of these electron trajectories that I mentioned. You have short trajectories, the electron go away, come back very quickly. This leads to this collimated radiation with long coherence time. And you have longer trajectories leading to this divergent radiation and reduced coherence time. You have dephasing on these long trajectories. So we understand much more, but we still don't know the answer. Is there phase locking of the harmonics? We think it is happening due to the theoretical understanding, but we want to have the experimental proof. And this really was thanks to the two groups and the two persons that shared the Nobel Prize with me. Group of Pierre Agostini could measure the pulse duration of the pulses in a train of pulse. I will describe the technique in a moment. And Ferencváros, using very nice laser development and going to very, very short laser pulse of the order of 5 femtosecond, he could both generate single attosecond pulse and measure the duration. Here is duration of 250 attosecond. The present record of the duration is 19 attosecond. So this is where we are. Both utilize a technique, a cross-correlation technique based on laser-assisted photoionization of a gas. And both techniques are actually quite similar, and I'm going a little bit later to describe this technique. Just to conclude this part, just a few words about where are we now? Are we still working on making attosecond pulses? Yes. Are we still working on optimizing high-order harmonic generation? Yes, and many things happening. First of all, you have a lot of progress in laser technology with a new laser system with really high average power and high repetition rate called ytterbium. You see that now we work with repetition rate of 100 kilohertz. We started with 0.1 hertz. This is an enormous improvement. And then we have also a technique to shorten these pulses, which are a little bit long for what we want to do, 200 femtosecond. So we can use, for example, post-compression techniques where you spectrally broaden laser pulses using cell phase modulation in a gas or in bulk, and then you compress this pulse, here using what is called chirp mirror. We also learn to control these electron trajectories using multiple wavelengths, using pulse shaping, so there's a lot of improvement. We can increase the conversion efficiency, we can increase the spectral range, and we can also create harmonics with different polarization states and even with orbital angular momentum. And finally, we are also improving our understanding and the way we can control phase matching. And this technique is really very flexible. We have harmonic setup which are very compact, others which are very long. We can work with high pressure gas jet or long, low pressure cells. So there are several ways to make this work. So I'm coming to the last part of this talk, which is a study of electron dynamics. So now I'm going to, it will be more atomic physics. And I'm going to talk about actually only a single process, which is called photoionization, where you send XUV radiation and an atom, and you emit an electron. This is the photoelectric effect, which was explained by Albert Einstein, 1905. This is even why he got the Nobel Prize, actually. Einstein was trying to understand thanks to his discovery, we could really describe light in a different way using photons, using what was introduced by Max Planck a little bit before. So I think this was an important work for the beginning of quantum mechanics. Now, we are going to concentrate on the photoelectron here. Probably you think of the photoelectron as a particle. Going to a detector, you can measure its energy, momentum, click, right? But we know it's also a wave. And what we can do with our technique is to characterize its wave properties, or even, as you will see towards the end, its quantum properties. So how do we do that? We use our attosecond pulse trains. In the frequency domain, it's a frequency comb of high-order harmonics. If we ionize an atom using this light, we will create electrons at different energies. If you do that, well, you will actually not learn anything about wave properties or temporal dynamics. It's really static, right? So we need something else, and this something else is a fraction of the laser used to generate these harmonics. This is our probe field. So in the time domain, you have this is an optical wave. Now, thanks to this additional field, we can now have two photon ionization process, where and we can get these sideband peaks here in red. So here, a sideband is created by absorbing one harmonic plus a laser photon, or the next harmonic, and then stimulated emission of a laser photon. So suddenly we have a quantum interferometer. We can go to this sideband by two quantum paths. Quantum mechanics, we add the amplitude of these two processes, and then you square. So it will depend on the relative phase between the two quantum paths. Now, we would like to have something varying, and what we vary is the delay between the attosecond pulse train and this optical probe field. This technique has been called rabbit reconstruction of attosecond beating by interference of two-photon transition. Why this name? It's because we follow the tradition in our field of ultrafast optics, and they call all diagnostic method by animal names. Maybe you have heard of frog, spider. These are diagnostic techniques, and so Agostini and his colleagues that really demonstrated this technique for the first time, 2001, called this rabbit, based on a theoretical idea by the group of Alfred Mackay in Paris. Now, how do we do that in the lab? First, we need an optical interferometer, which in our case is a Mach-Zehnder type of interferometer, The laser is coming here. We split into two. In one arm, we generate high-order harmonics, attosecond pulse train in a gas, and then we remove the fundamental field here. And then we have a probe arm with a variable delay stage. The size is something like this. It needs to be extremely stable. Now we really want to have attosecond precision. Typically we manage to have 20, 30 attosecond precision. So this is where the technique is in this field, is to make this very stable interferometers. And then we send this field, remember this is our tool, into a gas, so a chamber with a gas, and then we look at the electrons which are being emitted by electron spectroscopy. This is a typical what is called rabbit spectrogram. So it's electron spectrum as a function of delay, and what you see are bands due to absorption of the harmonics or the side bands, and really the information is in this oscillation of the side bands that you see here. This is where we get the time information or phase information. And the distance between two maxima here is again half a laser period. Titanium sapphire 1.3 femtosecond. So what are we doing? We are creating an electron wave packet. I represent that in blue here by absorption of this comb of high-order harmonics or train of attosecond pulse. And then we probe not only the intensity of this wave packet but also its phase or phase variation using this interferometry technique, using this infrared laser pulse, and looking at the sideband oscillations at different energies. So we can write this interference signal, something like this, with a delay, and this is what we measure. This delay depends mainly on two terms. One, which is the group delay of the excitation pulse, and this is why this method was utilized in the first place to determine the group delay of the excitation pulse and consequently the pulse duration of the attosecond pulse. But there is also an additional term, which is most often much smaller, which is the group delay due to the ionization process. And this is what is telling us what is happening to this photoelectron. We have two unknown quantities. In general, this term is very small, so we can determine this. When this is the term we want to determine, we try to eliminate this by making difference between two gases. One of them, you know what is this. In other words, we do calibration of our experimental setup. Physical interpretation of what is this group delay. It's actually a concept which was introduced by Eugen Wigner in 1955. Wigner was a theorist. He was looking at scattering processes and introduced as a pure theoretical concept. I don't think he ever thought we could measure these things, but he introduced this group delay as a derivative of the scattering phase. So here we don't have a full scattering process, we have half a scattering process. We look at photoionization. This is why you have this factor 2 here. Physical interpretation, it's really the delay, the delay for the electron to propagate out of this potential. Let's take an example. Photoionization of xenon in the 4D shell. This is actually a very old measurement performed in 1964 using spectral lamps. And what you have is a cross-section as a function of photon energy. And you see a beautiful resonance, which was actually interpreted by Joran van Dien in the 70s, a Swedish scientist that both Steve and me know very well. And he called that the giant dipole resonance of xenon in the 4D shell, and interpreted this as collective effects in the 4D shell. We would like to do dynamics of this phenomena. Can we go from the time to the frequency domain? Well, we would like to do a Fourier transform from the frequency to the time domain, missing the phase. Or we don't care about an absolute phase, the phase variation or group delay. And this is exactly what we can measure using our technique. And this is results of these delay measurements. Just we can scan half of this giant dipole resonance. This is for 43.5 and 45.5 electron. What you see is these positive time delays, typically a few tenths of attosecond, which are similar for both electrons. The black curve are theoretical calculation performed by Eva Lindroth using random phase approximation with exchange. The interpretation is this is due to the giant dipole resonance. We also have something happening at threshold, much longer delay, which we think are due to spin flip dynamics at threshold. And thanks to these measurements, we can really understand in the time domain this ionization process. And in this region of the giant dipole resonance, we have a relatively short trapping of the electron, while at threshold, much longer delay of the electron as it propagates out, which we think it's due to some spin flip dynamics. Let me say a few words about our work regarding Fano resonance. So it's very nice to couple to Hugo Fano, which was the first to get to do this Rosenthal lecture. So here we look at helium in a much narrower spectral region using absorption of one harmonic, not a combo of harmonics, but in a region which is close to a doubly excited state in helium. So what we have here is really a very nice example of quantum interference in atomic physics, where an atom can be excited either directly, can be ionized directly, or first excited and then auto-ionize due to configuration interaction. And this is really a process which was studied, which was really interpreted by Hugo Fano. Very, very nice article from 1961. This process has been studied using synchrotron radiation for decades. What we can do, thanks to a technique, is now to really, again, can we measure not only the intensity of this wave packet, but also its phase through the same technique, this interferometric technique. And these are the results. Both for the amplitude and the phase, we can measure a very nice interference pattern for the intensity of the amplitude, and we can measure for the first time actually the phase variation across this Fano resonance and its pi phase variation. When we have both phase and amplitude spectrally, we can go in the time domain by Fourier transform. Actually, we can do something even more interesting, which is we can give a time frequency representation of this photoionization process. And this is what is shown here using a tool which is a Wigner distribution. This really tells you how photoionization takes place both in the frequency and time domain. So here you have this energy distribution as a function of time, And what you see is that at short times you have mainly direct photoionization, and this is broad in frequency and short in time. At some middle time here you have a strong interference pattern. This is when these two processes have comparable amplitude and really interfere. And then at later time you have mostly this excitation and then autoionization process. So we can follow in time this photoionization process. At that point we thought, okay, can we always do that? We are thinking of photoionization as a fully coherent process. We're thinking of this photoelectron as like an optical wave, but it's not an optical wave, it's a matter wave. And then you have several processes, so in some case you have incoherence. So can we do better and really measure the quantum state of the photoelectron? So let me show you now this rather recent work. What we came up to is a slightly different method to measure actually the density matrix of the photoelectron using a bichromatic probe. So it's a bit similar. We have a pump, a single harmonic in this case, creating this electron wave packet, and indicated in blue here, and we analyze this wave packet using a bichromatic probe with two frequency components, omega 1, omega 2. So similarly to Rabbit, what we do is we project this state on a sideband, and we are looking at the energy of this sideband. Just to explain the idea a little bit, I'm going to split this XUV photon into two, part of the same pulse. This is a broadband radiation. So now you see that, again, I have two quantum paths leading to the same final state. This final state epsilon f here can be reached by absorption of this photon plus the red photon, or this one plus the orange photon. So if I study this sideband as a function of delay, I'm going to see interference. And this interference pattern is going to depend on, for example, if there is a well-defined relationship, phase relationship between these two states, epsilon 1 and epsilon 2. So it's going to tell us about the coherences of this electron wave packet. So if I put that with equation, the interference pattern will look like this. Instead of 2 omega, I have now delta omega, the difference between the two frequencies. And the contrast of the oscillation is going to be proportional to the coherences of the density matrix, while the phase is going to be equal to the phase of the element in the density matrix. If we vary omega 1 and omega 2, we can span this electron wave packet. So we do a tomography of the electron wave packet. We do a quantum tomography. We call this technique Kraken. It's kind of a bad algorithm. It's not algorithm, acronym, using Swedish to get the K. But this is the name. Yeah. So these are examples of measurements. What you see here are interference patterns for different bichromatic frequencies, omega 1 and omega 2. And from this we can determine the subdiagonals of the density matrix. It's a density matrix energy and energy. We are in the continuum. And from these measurements, we can get this different subdiagonal. We can also measure the diagonal and also the rest of density matrix by symmetry. From this type of measurements, we do an interpolation using actually talking to our friends in quantum information, and they help us to apply an optimization procedure to recover the density matrix. What do we see? We see a round density matrix. No surprise, this is a density matrix of a pure state. In this case, ionization of helium, far from any resonance, leads to this very pure state. We can measure the purity, and we find it's very close to 1. Let's do the same thing in argon. And I think this is how this seminar was announced with this picture. This is what we get. It's not round, it's oval. It's the density matrix of a mixed state. What is happening in argon? Now we do a little bit of basic atomic physics here. We have the spin-orbit interaction leading to splitting of the ionization threshold here. The ion can be left into 2 different spin-orbit states, p1/2 and p3/2. This leads to entanglement. We create entangled ion-electron state when we photoionize argon, as shown here. Since we only look at the photoelectron, we lose information. What we measure is the reduced density matrix, and this is why we get this mixed state. The purity that we measure is 0.65. If we had maximal entanglement, which would happen if there were no overlap at all between the 2 electron distribution here, which means that this would be 2 blobs, then the purity would just depend on the statistical ratios between the 2 spin-orbit states would be equal to 0.55. So we are not in this situation because we have a small overlap, and if you have an electron which is born here, then you don't know what is the state of the ion. If the electron is born here or here, you know the state of the ion. Here we don't know. And you also see that what we would like to do, among many things, is to change the bandwidth of our XUV pulse, to change the degree of entanglement that we have. So I'm coming to the end of this talk. Let me just say that attosecond science is very open field at the moment. I have shown you what we can do in atomic spectroscopy. Challenge of our field is to really use this technique in chemistry and condensed matter physics to really look at these electronic transitions taking place in the time domain. There are a few industrial applications, and there is this very interesting interface that we see at the moment with quantum physics. There are also new ways to generate attosecond pulse. There is very interesting progress with free electron laser light. Since a couple of years, they have learned to produce attosecond X-ray pulse. Very complementary. The pulses are in the X-ray domain, high energy per pulse, higher than what we can achieve through high-order harmonic generation, but also is really far from being a tabletop setup. So I think these are very complementary source. And just a couple of days ago, I had the pleasure to visit LCLS for the first time, and it was really very interesting. So with that, I would like to thank my group that you see here in Lund, and I would say thank many researchers over many years, and also a lot of collaborative work that takes place in this field. These are the list of the senior researchers working with me on this subject. Of course, I need to thank the organization funding this research, And finally, I would like to thank you for your attention. Yes, actually, I liked it because it's really coupled to what I'm saying, right?
So, questions? Don't be shy.
Hi. So, I guess in the attosecond world, light moves pretty slowly. So, when you have your tabletop interferometer set up, do you have to be really careful about having like exact distances between things? How do you manage that?
Yes, active stabilization and no vibrations. Yeah, all of that, and we're still progressing on these things actually. Yeah.
So it's three nanometers.
Oh, 30. Yeah. No, it's 3 nanometer per attosecond. Yeah, you're right. But since our precision is tenths of attosecond, the precision we need in spatial is about a few tenths nanometer.
Other questions?
Yes.
So this process of the electron coming out and that, how does this depend on what kind of atom you are looking at? Like how many electrons and how many neutrons?
This is a very good question. We're working almost exclusively using rare gases, and the reason is that this happens when you need to have atoms which are resistant against ionization. So, if you use alkali, for example, then your electron is just absorbing with 1 or 2 photons, and that's it. You don't have this strong field regime. So you want to have atoms with high ionization energies, so they can feel this high intensity. And we usually it's only one electron in the outer shell that is doing this, not several. Yeah.
Yes.
There was recently some advancement in using AMO setups for nuclear excitation with atomic bombs.
Yeah.
Do you think it might ever be someday possible to do this kind of analysis with nuclear excitation instead of atomic?
What was very interesting in the work you talking about is that they were actually using the 7 harmonics. So they use one of these high harmonics to do that. So your question is, can we use this for? I would say yes. It's one thing that remains to be done, and I think that was done for the 7th harmonic in the group of Yun Yi, I think, is to make this XUV frequency comps. And this is still very difficult. You need to put your atomic gas in an enhancement cavities and get this extremely narrow bandwidths in the XUV. This is still, I think, to be done. So there are many things to be done for young people here. Yeah.
Last question. Oh, next slide.
You said on the last slide that this would be a very powerful technique in like advanced nanophysics. What is some of the current work being done in that area? What are the biggest challenges of bridging that gap from atomic to
I think there are 2 ways to do condensed matter physics with these techniques. One is to do actually a high order harmonic generation in the solid, in the crystal, and you get information about the bond structure of the crystal. This is called solid HEG, solid high order harmonic generation. The other way is to use this radiation to look at photoemission and measure these delays not in gas, I have shown, but in solids. There are also problems and difficulty. I would like to say that. So this these are becoming huge field of research, actually. One, I think, challenge a little bit that remains is the possibility to combine this type of temporal resolution with good enough spatial resolution. There are techniques using PEM, and this is photo emission electron microscope, but it's still a little bit under development. So again, many things to do.
Okay, thank you for a beautiful talk. You obviously worked very hard for a long time and made incredible progress. So I want to ask a more personal question. Have you ever hit a moment when you felt very discouraged, or like you couldn't get past a hurdle or some other problem that you then overcame? I'm thinking about how all of us in physics always hit these moments, and we don't imagine going on to great success.
I can mention two such moments. One was before my colleagues managed to measure attosecond pulses. It was not clear at all how to do that. You see that it's rather complicated. And we were actually going into using a different approach called autocorrelation, so measure the light with itself. But this was very difficult, and it turned out to be not the right way to do. So at the end of the 90s, it was a little bit, it was a difficult time, which was really, thanks to my colleagues, we came through that. I can mention that this Kraken technique that we have developed, it's already 2-year-old. We're trying to make it better by using actually not only 2 colors, but several. We call it polykraken. So with the idea that we should be able to do a measurement at once of the density matrix. Not only we have to do many measurements, but make it at once. And it's really difficult. we are facing a new problem. At the same time, we are learning, but it's much more difficult than we thought. But we are going through that. But what maybe more generally I want to say that to have problems and setbacks, it's belong to research, and somehow we have to accept that this happened like that. And when we go through this in general, then it's. First, you learn new things, and generally it's getting better. Yeah.
Okay, it's a good note to end on. Thank you very much.
Thank you.